Our next speaker is Zhaoran Wang. Zhaoran is an assistant professor at the Northwestern University, and he is a JP Morgan Research Fellow in the Reinforcement Learning Program.
Well, thank you, Prasad. So I will talk about learning representation in reinforcement learning. So this is a new paper on NeurIPS, and it is joint work with my student Yufeng Qi, and also Zhaoran, who is a research fellow here, and also Yongxin at Georgia Tech. So we have seen a lot of empirical success of reinforcement learning, especially deep reinforcement learning in practice. So the key is, so temporal-difference algorithm, which does policy evaluation, and also Q-learning algorithm, which does essentially policy optimization, turns out to be very powerful when they're combined with neural networks. So we have seen a lot of examples like Atari Go and robotics and autonomous driving. So the key success there is a combination of the representation learning ability of neural networks, which essentially maps the input, which could be a very complicated object like an image, to some latent space, which is much simpler for developing the policy. So it is combined with those reinforcement learning algorithms. So the major theoretical challenge here is that, well, in the classical literature, we know that nonlinearity is essentially incompatible with reinforcement learning, especially, for example, in temporal difference learning. So I will talk about why in a moment, but this barrier essentially causes many trouble. So if we have a nonlinear function approximator like a neural network, which is nonlinear in the parameter, so we will have non-convexity, which makes it difficult to obtain the global optimal solution. And more importantly, it could cause divergence. So the algorithm could just diverge and not converge at all. So the question here is that how do we actually characterize the evolution of the feature mapping? So in the classical literature, we assume this is fixed. In this work, we show that if we're using a two-layer neural network and it is sufficiently over-parameterized, we can not only obtain the convergence, but also get a global optimal representation. So the tool we use here is optimal transport, which is also used in supervised learning setting, but there are some differences. Next page, please. So the policy evaluation problem is that we want to get the expected total reward starting from a certain state and action given this policy. So the way we try to estimate this Q pi is to minimize the projected mean square projected Bellman error. So T pi here is the Bellman operator. F is the function class we're interested in, which is the class of two-layer neural networks, which are over-parameterized. And D pi is a stationary distribution induced by pi. Next page, please. So the temporal difference learning algorithm essentially looks like a stochastic gradient descent algorithm running on this mean squared Bellman arrow. So because Q is a neural network, there's non-convexity, and also there's this bias of semi-gradients. So this together leads to a divergence, which is known like in the literature. Next page, please. So in this paper, we're considering a two-layer neural network where alpha actually controls the magnitude, and the number of neurons m would go to infinity. And rho here is the distribution, and also it has a one-to-one correspondence to the representation. And here we're considering over-parameterization, where the width goes to infinity, and we are trying to tune this alpha, which we'll call over-representation, to make sure the convergence happen. So next page, please. So essentially, we show that if we just using a mean field analysis, then we can establish the convergence of Q function and also rho, which corresponds to the representation at a 1/t, where t is the number of iterations. Here we're considering continuous time, as the t is the time, and also alpha appears in the error bound, and if alpha is large, then this error would go to 0. So this is this is different from the neural tangent kernel regime, where we can also characterize the evolution of the feature of the representation rho, whereas in the NDK regime, the rho is essentially fixed. So the key is just the first variational formula in the Watson-Stan space. So that's the, I think that's everything.